Okay, so now we have Natalia Rektsini talking about hunting for free-floating planets with Euclid, and so that's another instrument that can be used. And these last two talks are actually quite important because this is where a lot of the people in this room can help make the case that free-floating planets are important, and get the case that make a strong science case for these observations from additional telescopes to roll on.
Yes, that's right. Hello, everybody. Can you hear me? Oh, well. Thank you for having me here. It has been a pleasure finally being in Japan, in Osaka. I'm Natalia. I'm a PhD student at the University of Tasmania and also the Institute of Astrophysics in Paris. For the purposes of this talk, I'm going to remove my Australian summer hat because, it's winter here and it's useless. And I'm going to put on my European hat and I'm going to discuss about kind of what Farzana also already mentioned, but this time with two satellites, Roman and Euclid. And this talk, I'm giving this talk on behalf of the Euclid Exoplanet Science Working Group. This name appeared like this month. Up until now, it was just people fighting for this. Now we're finally having a group. I am a very, very early unofficial member. It's a hat issue. Soon, hopefully, I'll be official member. So yes, I'm presenting a lot of work that all these people did. And I'm going to start with talking about Euclid. So Euclid is a European medium mission. During lunch, I figured out that this means that it's about less than €1 billion budget. It's a 1.2 meter telescope. It has been launched on the 1st of July 2023. It orbits around the Lagrangian 2 halo point. It has a field of view of 0.55 square degrees. It can reach with good certitude magnitudes of 24, maybe even 25, but don't quote me on this. And its main purpose is to map the universe for dark energy and dark matter. In the early stages, Euclid was supposed to have also a gravitational microlensing survey. Unfortunately, cosmologists threw us out. And so now it has two main surveys. So it has the Euclid-wide survey, which is basically all these blue lines that you see here. They want to basically measure the size and the properties of 1.5 billion galaxies in 6 years. This is quite ambitious. And it takes 65% of the Euclid time. Then they also have the Euclid Deep Survey, which you see in the small yellow and red dots, which takes about 17 times. Then they have a little bit of time for calibration and all that. And then there is this 9% of unallocated time. This is due to the fact that the fields of the wide survey are not homogeneous. So there are a lot of times where basically they cannot do their survey. And in this time, they can use the telescope to do calibrations and, test their instruments, but also they're open to other scientific reasons, help with other science. It has two instruments, the VASE instrument, which is an optical imager. It has 36 detectors of 4,000 times 4,000 pixels. It can reach down to 0.11 arc second per pixel, and it's a single V wide field. So basically, this instrument was the high angular resolution instrument that they built in order, they measured, what is the size of the galaxies that they were expecting. And then they also have the NISP instrument, which is the near infrared spectrometer and photometer instrument. So it has a photometer and a spectrometer, and it covers Y, J, and H filters. It has less resolution, but it can be useful. And this is basically to, I think that they did it to cover the redshift of the galaxies and go deeper. So as I said, it was launched in July 2023. It's supposed the main mission, the main survey is 6 years. Unfortunately, they had a lot of issues starting. They had problem with the guiding because the detector will follow cosmic rays. It was kind of an engineering issue. They solved that. Then they had problems with the solar panels. This has never, well, they figured out ways to solve this, but they lost a couple of magnitudes. And also this means that the solar aspect angle limitations restrict monitoring of targets near the ecliptic for maximum 23 days. So they lost all this time, about a year on the survey. So they started later, which means that the survey is going to end later. And this is just a typical reference observing sequence for Euclid. It's basically the core of the whole mission. This is what really enables them to do the high resolution that they need in order to use the weak lensing and monitor the galaxies. And now here comes us. So because, they dropped us out of the project, but well, in Europe, we don't like, So there are a lot of people that they decided to go on and do detailed studies and build scientific cases about how we could use Euclid for gravitational microlensing. And there are a lot of works here. Some of them the most recent ones, I'm gonna mention them today. Again, this is a work that, it has been going on way before I knew what an exoplanet is. So it's kind of stressful for me to present their work, which is very important. During this more than a decade, they have built two main strategies, two main surveys for Euclid. The first one is a single epoch precursor optical near-infrared survey of the Roman fields. So basically observe the Roman fields with Euclid years before the actual launch of the Roman Space Telescope. And with these, we can use it to have precise mass and distance measurements for the bounded planets. And then the next step will be to have a joint survey between Euclid and Roman. So basically what we ask here is for them to stop what they're doing and look toward the galactic bulge with us for multiple days. I have been told that I'm allowed to say that Euclid decided to give us time for the precursor observations, which is a huge deal. And I'm very excited about this. This has been, again, a lot of work for all these people to actually convince them to do this. This is going to be in March. It's going to last we're going to have 45 hours of Euclid observations on the Roman fields. And this is during the unallocated time that I showed before. ESA shows they're suddenly very happy with us. So, we're ready to go to the next step and actually ask them for the joint survey. But a few words about the Euclid observations that we're about to have. I'm not going to go into a lot of details because they're still under discussion, and I assume that also, given that the Roman fields are not yet read, there are going to be a lot of discussions, but basically we're going to get 4 reference observing sequences per frame, which means that, well, here I say 43 hours, but they gave us another couple of hours because the telescope is going to be tilted, so the PSF model, it's going to be more difficult to construct the PSF model. So they gave us more time, which is really amazing. And these observations, they will allow us to use pre-follow-up observations of the Roman fields in order to deduce the precise mass measurement of the bounded planets. This is work that I have been doing, David been doing for years, Sean, Aparna, Naoki students have been doing with KEC and HST. So we kind of know what we're doing. Unfortunately, this works also. I should say that with Euclid, we could also do these observations now for exoplanets that have already been founded with previously. So anyway, but unfortunately, this works great for bounded planets. It's not really working for the free-floating planets. But what you can do with the free-floating planets, as we have seen on the first day from Sean, Terry, David, Aparna, and also works from Tremek, is that we can search for a lens that maybe, oh, okay, this planet is actually in a wide orbit, so maybe there is actually a star that is moving around. So this is what we could do with the Euclid Precursor observations, but not the mass measurement. And this is why we really, really want the joint survey. Now, you've seen the microlensing parallax before. I think that maybe the non-microlensing people, they don't really understand what the microlensing parallax is. I hope that maybe this plot from BAN 2020 gives you an idea to understand that literally the difference between the two observations, like the observation points, helps us make a difference in the light curve, and it's really related to the mass and the distance of the lens. So in this case, the free-floating planet. And okay, so to, you want to ask Euclid to drop what they're doing and come join us, you have to show that actually, yes, this can work. So Bachelet and Penny et al., they have made some simulations similar to what Farjane showed before, to show that depending on the photometrical precision of Roman at the baseline, can Roman alone use the microlensing parallax to deduce the precise mass of the free-floating planets? And they found that it won't be able to do it for events that last shorter than 4 days. This is a really big mass. So it won't help us to do it for the low mass free-floating planets. And they have studied cases for different observational cases, and they have showed, we can see it with black, that if we have Euclid and Roman, basically, yes, this is when we can actually go to the low masses. The next issue that everybody keeps asking is, okay, but are they in a large enough distance? So they have also studied this. We don't know exactly the distance between the two telescopes, but they simulated using the Gaia satellite and Euclid satellite, because they're both in O2. So we assume that the minimum distance will be around 100,000 kilometers. I can reassure you, I don't think that they will be closer, because that's very dangerous. And they have shown that basically, even if we are around 200,000 kilometers distance between the two telescopes, still we can go pretty low in the sensitivity. So yes, this is worth doing. Finally, in a most recent paper in 2022, they have simulated light curves for 3 cases, for Jupiter, Saturn, and super Earths. And they have shown that this was made for distances that are around 300,000 kilometers between the two telescopes. And they have shown that basically we will be able to constrain around 90% of the Jupiter masses. They didn't do it for the Saturn masses, but I think it's kind of the same. And for super Earths, in cases where we have finite source effects, it can go up to 89% of the events that we're gonna observe. So basically 89% of super Earth masses, free-floating planets detected by both Euclid and Roman will have a precise mass and distance measurement. This is really huge. I don't know if I can make it clear enough. This is why we really need it. So my takeaway point is that these are two telescopes that they really complement each other. They're going to be up there simultaneously. And this is the only way that we can actually go detect low mass free floating planet and actually be able to say, yes, this is a free floating planet. And we're gonna, the French people are gonna try to, well, they're gonna suggest to Euclid that let's try to do this for the first microlensing survey observational season. And I don't know how will that will go. The thing is that these are people that, we're 20, 30, maybe the whole microlensing community, 100 people. This is not enough. I think that we all the exoplanet community needs to understand how important this is, what an extraordinary chance this is to have these two telescopes up there. And if we all try to ask them to do this, because the time is now, we have been talking, people have been talking about this for a decade now, but now this is actually happening. Now we are actually going to propose this. And if we're all together, I think that I do have chances to convince them to do this. So there are different science scenarios. One is to ask them for, depends, 23 to 30 days of simultaneous observations. And this will be during the second or third Roman observation season. So basically, Euclid will still be in a survey mode. So we will have both NISP and VIS instruments. And this will also help us understand better how to organize the observational seasons, the next observational season for Roman. Then the other possibility is to ask for 23 to 30 days at the last season of Roman, where basically Euclid will be in the extended mode, but this means that we will lose NISP. We only have VIS, which is good, but it's not great because you want to have the near infrared. And my personal favorite is to ask for everything. So I think that it's important to get the second or third observational season of Roman to get at least 20 days of Euclid. And then we will discover. I'm not putting numbers because I think throughout this whole conference, we have realized that yes, we're gonna discover free floating planets. And yes, there will be low mass free floating planets. And if we don't do this, we will still have these conversations and these discussions about, oh, maybe the ground basis, there is an error. Oh, maybe there is this. This is the way to actually get answers. Probably these answers will give us more questions, but at least we will know that it's not errors, it's not uncertainties. These are real, observations. And with this, I'm gonna close, and I'm gonna really ask you to not think about this just microlensing. This is about science. This is about free floating planets. And I think that the whole exoplanet community should be together on this and ask the cosmologists and the European Space Agency to give us time and do some cool science. Thank you.
Questions? Important topic. No?
You mentioned that Euclid has changed its observing strategy because of the stray light. They have to avoid some directions in the sky. Does it affect the 30-day long survey of the galactic range?
No, I haven't worked on this, but they have made sure that throughout the precursor observations and the joint survey, there will be no harm done to the instrument. So, oh yes, that's why I'm not sure about the time, the dates. It might be 23, it might be 30. It depends.
More questions?
Hi, great talk. maybe I just need to read that 2022 paper again, but the expected sort of percent, 89% of super Earths can be recovered with finite source effect. There was a delta chi-squared metric on there that shows an improvement. So it was significant improvement over like 2,000 delta chi-squared for the super Jupiter. Saturn was like a couple hundred delta chi-squared. Super Earth was like 58 delta chi-squared improvement. Is that just on the difference between what? So the Roman and Euclid both measure maybe finite source effect, but what's the difference in the delta chi-squared measured against? That my question makes sense. Because theoretically you get they both have finite source effects.
Yeah.
But there's there's a parallax signal also.
Yeah.
So there's a shifted difference. So is it just measured? Is it measured on that metric how different maybe the T naught position is or something?
I think they were if I remember correctly, they did it whether there will be for different cases. So I'm not sure which delta chi-square you're talking about, because I think they had it if we had finite source effects, finite sorting effects, and microlensing parallax, none. So for the super Earths, I honestly don't remember exactly. I think it was dropping. I think it was. I do remember that it was. Well, also, it's not my work. I'm just reading the paper and working on the paper, but different thing. But if I remember correctly, it really drops a lot for the super Earths. Actually, I think it's pretty impossible to have accurate mass measurement without the microlensing parallax and with only the finite source effects. I think the error bars are really huge. Yeah, it's not going to be the same as here. I think actually that
the one on the right, that delta chi-squared 51.
This is without the microlensing parallax. This is only with Euclid. This is only with Roman. So with one.
Oh, okay.
Yeah, sorry, I didn't explain it. Yes, with one, it's what you have without Roman and without Euclid, and the other is what you have with Euclid and Roman.
Any other questions?
So this simulation includes both near infrared channel and visible. And also another question is why we can use the near infrared channel in the last slide?
Because I think that the NISP detector will be out of use after the 6 years of the survey, the Euclid survey. So they will only have the V's. That's why.
And this simulation includes both.
Yes. Yes.
Questions?